Today, I'm gonna talk about how to graph a higher degree polynomial and what are the properties for it so that the property can help us predict the pattern of the graph. Here are some main vocabulary for this section. There are local maximum, minimum, roots, y-intercept, and end behavior. So the general definitions for this are y values that are bigger or smaller than the relative point, roots, where the graph crosses the x-axis, y-intercept, where the graph crosses the y-axis, and at last, for end behavior, is the y value that follows the x value. So here is a graphing example for the vocabularies. And the roots for this graph are -3, 0, 2, 0, and 5, 0. And the only y-intercept for this is 0, -2. And here are the local maximum and minimum. So how to compare the local maximum and minimum? We only have to grab 2 points that is close together here. So here is 2, 0, and I think it's -1.5. Yes, so comparing these 2 points, you can see that obviously 2, 0 is bigger than -1, -1.5, -4. So this one is going to be local minimum and this one is going to be local maximum. So same as these 2 points. And for the end behavior, it is when x goes to positive infinity, the y value is going to be positive infinity. And when x goes to negative infinity, it's going to be positive infinity. So the end behavior, it's not always going to be about infinity. The y value can sometimes be constant. So for example, if you have a graph that is a vertical line, it can be like when x value goes to positive infinity, the y value is going to be 1. And here are the properties for the higher degree polynomials. So let's start with even degree polynomials. So the graph are always in U-shape, so as well as parabolas, and the end behavior is either go to both positive infinity or both go to negative infinity. And when the degree increases, the graph will become narrower. And at last, the leading coefficient has influences on concavity and also the width of the graph. However, these 2 points about the width of the graph, it's not going to be the same. So here is an example for what I just said about that. So the standard, let's take y equal x squared as the standard of the graph. So as you can see, it has one root which is 0, 0, and which is called like vertex at this point. And this is a parabola here. And if the leading coefficient is -1, it's gonna be concave down. So the leading coefficient has the influences on concavity. And if you increase the degree, such as become x to the power of 4, which is the blue line here, the vertex point, it's gonna be flatter. So as you can see, it's almost like it don't have a clear vertex for it. And for the leading coefficient changes the width of the graph, it's gonna be narrower, but they still have the same flat vertex. So here is the odd degree polynomials properties. So they are all similar to the graph of our standard cubic polynomials, and I will show you about the graphic example on the next slide. And the end behavior, it's either gonna be when x go to positive infinity, y value is gonna be positive infinity, and when x go to negative infinity, y value is gonna be negative infinity. So they are always the opposite side. And when the degree increases, the graph would become closer to the y-axis, and the leading coefficient can change the direction of the graph and the width of the graph. As well as the even degree polynomials, they are all the same. So become closer to the y-axis doesn't mean that it's gonna be narrower. It's different from the leading coefficient influences. Ooh. Okay, here is one example for it. So the standard graph for this one is gonna be y equal to x cubic. So here is the standard cubic form. And if we add n2 leading coefficient to it, it's gonna be like green line. So as you can see, it has the same width on the x-axis, but it somehow become narrower when it drops. So if the degree increases into y equals x to the power of 9, it's gonna be flatter on the x-axis part. So it's almost become a 90-degree angle. And if you add a -1 leading coefficient, it's gonna flip over to the next side, the other side. So it's gonna be a symmetry for the y-axis. And that's all. Thank you for watching.